Hello, I'm Jack Shafer, and Bob Stalick and I will be talking about and demonstrating the assembly and flying of indoor model gliders. Bob will start off showing the assembly of models from a commercially available kit, and I will follow with a discussion and demonstration of building a model from scratch. And building a model from scratch means cutting out the parts from balsa sheets and then assembling them. This part will include a plan for a simple model, and it will also demonstrate the actual layout and cutting out of the parts. The assembly of those parts will be covered adequately by what Bob does in his assembly segment. The models are quite similar, and what works for one should work pretty well for the other. Both models conform to the 2013 Science Olympiad rules for their elastic launch glider event, and since they do conform to that event, they also conform to the rules for the Academy of Model Aeronautics standard class catapult glider event for indoor gliders. The AMA catapult class is for people who are interested in the regular model airplane contests as opposed to competing in the Science Olympiad events. The DVD is being produced in support of the goals of the National Free-Flight Society Foundation, and those goals are to encourage and support the building and flying of free-flight model airplanes. Free flight in this case means that there is no control of the model from the ground during its flight, no radio control, and no control lines. The National Free Flight Society has a website, freeflight.org, and on that site you can find listings of hobby shops across the country, model clubs, suppliers of parts and equipment, and listing of publications and plans that are available, plus other information. The kits being used in this production were contributed by Stan Buddenbohm. Stan is a well-known and very expert builder and flyer of model gliders. He holds numerous records, and he is also a supplier of very high-quality kits. If you are interested in purchasing kits from Stan, his address and the website for the Free Flight Society will be listed at the end of the DVD. Before we get started with Bob's demonstration of the assembly of the kits, I want to talk about a very trivial seeming subject, pins. Bob uses a lot of pins in his assembly sequence, and you need to know a few things about pins. Most important is that push pins are not suitable for this kind of work. They tend to be too thick. They split the balsa wood. They leave big holes in the balsa wood, and are generally not such a good idea. You want something with a fine shank and a large enough head that it isn't painful to push it into balsa wood. I use some that I found at a, Walmart or some sort of store. Glass-headed, big enough that you can push on the heads without hurting yourself, and the shanks are thin enough that they don't split the wood too badly. Anyway, with that little bit of information, we'll turn it over to Bob.
Hello. My name is Bob Stalick, and today I'd like to take some time to show you how to build a kit for the Elastic Start Glider, or as I will undoubtedly call it several times during the course of the next few minutes, Catapult Glider. The glider that we're going to discuss today and show you how to build is from a kit that is produced by Stan Buddenbohm. Stan provides this kit along with the launching device for $30 plus shipping of $8 anywhere here in the United States. So we have a prototype kit here, and I'd like to show it to you. This is what it looks like when it comes. All the pieces are identified. You can see he's written on there what this is the bottom of the wing, and here's the launching device, and there's even some extra pieces in there for you to, in case you mess up. So this is how it comes. There are 2 gliders here, enough for 1 person in the event if you're flying in the Science Olympiad this year. It also comes with a set of plans. This is a copy of the plan, and his only recommendation is for preparing the model is a sanding block. This sanding block is equipped with 600 wet or dry paper, which is what he recommends. It also comes with a set of instructions which tell you not only how to build the model, but also how to trim it for flying. So without any further ado, I would like to go ahead and begin with the construction of the glider. The first thing he recommends is the use of cyanoacrylate, or Cya glue. Quite often this is known as crazy glue or instant glue, or words to that effect. My concern about the use of Cya is that it is, although it's a very good adhesive, it also can glue your fingers together or glue other parts of your body to other parts of your body, and this is not desirable. Suggestion by Stan is that you use nitrate or nitrile gloves. I'm going to build a model today using Cya, and I'm going to build another model using more standard adhesives, in this case Titebond or Sigbond. I'm using Sigbond today. These are glues that are available at most hardware stores, or certainly at your local hobby shop if you have one close by. So I'm going to start now with the gluing of these gliders together. It's a fairly simple project, and let's get started. Well, I want to begin with the wing, and what we're going to do before we glue the wingtips on is we're going to take some very fine sandpaper. This is 600 wet or dry paper glued onto a piece of aluminum, and we just barely round the leading edge. The leading edge is the curved part of the wing. We round it both on the top and on the bottom. Then we're going to pin it in place here on the plan. And we're going to do the same thing to the tips. We're going to gently sand the leading edge of the tips. This plan doesn't line up. Check to see you're sanding the leading edge just a little bit. This should line up right about like that. I've cut a couple of blocks of balsa wood, scrap balsa wood, to the proper dihedral angle, which is 1.5 inches. We're going to block this in place. In this fashion. We're going to put the dihedral angle in place in this fashion. And then we're going to use, this is the Cya, this is called Zap, and it's thin Cya. We'll just run a bead along this line where the two parts meet. it's important that the two joints are butted together as well as they can be butted. Now this glue takes about 5 seconds to cure, so this side is already done. We remove the dihedral marker, take the pins out. Now, although Stan recommends using thin CYA or ZAP for this operation, I'm going to use the thick stuff because it fills up the gaps, and I believe in this case that's an appropriate use of this as cement. So we'll put a little bit on this, rub it across to make sure we've got all of the glue in the right spot. This stuff takes about a minute to cure, and so in that time I'm holding this in place, and then I'll put the dihedral brace underneath it so that it sets in the proper angle. We'll do the same thing on this side. There's a little excess glue here. Stan suggests using a napkin. I like to use Q-tips. Q-tips are useful because you use them once and then you throw them away. And they do absorb the excess. They also help to rub the glue into its slot. This is probably close to being dry, but I'm going to let it set for a while and go back to the fuselage. So the nose piece is taped to this board. We'll take it loose eventually. We see that it's set up at that angle. We'll shape it later. But once again, we'll use thick CYA. We'll slide this in place. Use a Q-tip to wipe up the excess. And with a pin, we'll just pin this in place for now. The next step is to put the curved wing mount to the fuselage. Now that's this little section in here. It raises the wing slightly off the top of the fuselage, and it also is taped to the board. There is no difference in the wing mount's direction. It's equally. It's the same in either direction, I guess is what I'm trying to say. Poke myself, it appears. So we'll use the same thing. We'll use a little bit of the thick CYA. And we'll glue it in place. Okay, once that's done, he says next to do the rounding of the leading edge of the stabilizer and the fin. Those are also taped to the board, so I'll bring out one. There's the fin. It goes, this is the leading edge. We'll very gently sand that to round it a little bit. Takes care of that. This is stabilizer. This is the leading edge of the stabilizer, that point. We will round that as well, both top and bottom. What I found with the stabilizer is very easy to get it cockeyed when you glue it on. So we're going to use a marker, and we're going to mark the center line of the stabilizer on the plan right onto the stabilizer itself. Okay, so if you put the stabilizer on the plan, you'll see a line that runs in the leading edge right up here and also in the trailing edge. So when you glue this onto the fuselage, this will line up for you pretty well. So this part should be all done. We'll take the wing off the board, assuming that it's going to stay in one piece. If it doesn't, you can always re-glue it. Just like I'm about to do. So we'll let that cure a little bit longer. Now the fuselage part should be pretty well cured, so we'll unpin it. And check to see. It appears they are. Okay, the front of the fuselage is supposed to be the shape, or it's the diameter of a dime. So we'll put a dime up there and we'll mark around it with the pin so that we have at least that diameter. It can be larger than that, but there's no reason for it. We'll do some cutting. So if you have a little difficulty, as much as I had, with getting the wingtips to glue on correctly, one of the things I have used in the past to help with that is something called micro balloons. They're a very fine fiberglass material. You can buy them in hobby shops. If you can't find micro balloons, a good substitute for micro balloons is baking soda. You can sprinkle the baking soda or micro balloons right on the joint, smooth it out a little bit, use some thin Cya, such as this, and drip it in onto the micro balloons. Then pick up the excess using your handy dandy little Q-tip. So there you have it. These wingtips are pretty secure now. I've marked the center section of the wing, and we're going to glue the wing in place on this platform that you've already glued onto the fuselage. The secret here is to try to get it as even as possible. You don't want the wing tilted one way or the other on the fuselage. You want it as straight as possible. And that takes a little bit of doing. Probably it's a good idea to pin it in place, which is what I'm going to do here. Pin the leading edge. I've marked the leading edge center with a pen mark right there and another one right there. So we have the front and the back. We just line the two up. We're going to pin this in place eventually. Pin it right into this little up part called the pylon, actually. And we'll do the same thing in the back. We'll put some thin on here in the center. Let that set up. Then we'll do the front and the back. Okay. Now we'll try the front. Hold it in place. Some on the other side. Hold it in place. the same with the back. You have a little bit of time to work on it to make sure you've got it square. It appears to be square. Now I have to get my fingers loose. Okay, remove the pins. There you have the wing attached. Probably wouldn't hurt to put a little more adhesive on it, a few drops on either side, just to make sure. Use your Q-tip. Okay, there's the fuselage with the wing attached and with your launching point. The next step is to put the stabilizer on, and the stabilizer is actually put on, if you look at the plans carefully, a slight angle. The reason for that is that the angle of the stabilizer determines what glide circle is going to have. In other words, if you want it to glide to the right, you put the right side of the stabilizer higher than the left side, and that's the direction we want this to go. I'd also call your attention that there's a portion of the fuselage that sticks out behind the stabilizer. I've marked that with the pin. This is where you hold the model when you're getting ready to launch it. So next thing we're going to do is we're going to put the stabilizer in place. Usually what I do with the stabilizer is I center it to make sure I've got the center line on both sides. And I'll put it down right on the workbench in this fashion with the marks even. I've got the wing slightly tilted so that it's got that angle to it. The stabilizer has this angle to it. And then using the thin CYA, I'll put a couple of drops in place, hold it for a bit. When I'm sure it's okay, I pick it up, take a look. Does the stabilizer have the proper angle? It does not. I'm going to tip it so that it does. It has a little bit more of an angle now. Not quite yet enough. We have to force it just a bit. There we go. So now I'm going to finish putting a little bit of CYA on it to hold it in place. And make sure I've got that angle held in place while I put the CYA on it. Use a Q-tip, wipe up any excess. There we go. The final step is to glue the fin in place. On the plans, you'll notice that Stan calls for a little block of 1/32 balsa wood. He uses that to set the right turn along with the stabilizer tilt. So we're going to put that. I've glued that block in place already here. We're going to mount the stabilizer, the fin, right behind the back end of the fuselage, right on, basically on the same area where the stabilizer is located. That's glued alongside the fuselage. It's not glued on top of the fuselage. Once again, we'll use some thin CYA, hold it in place for a few seconds, finish the gluing, glue the same here where it meets the fin, use the cotton swab. And basically there's the glider. So at this point I'm going to stop with this one, I'm going to put it aside, and I'm going to build the other one, and we'll use a different kind of adhesive. We'll use a SIG bond, which is, or tight bond, which is carpenter's glue. It will take quite a bit longer for the glue to set up, but it should be just about as strong. We'll finish up both gliders at the same time after I've glued the other one together. The process for gluing the wingtips on and other parts of this glider using SIG bond or tight bond is exactly the same as using the instant adhesives, except it takes a lot longer to dry, and these glues are non-toxic. You can use them without worry of sticking yourself to the model or sticking yourself to yourself. And this also washes off with water. So if you're working with youngsters who are not accustomed to using cements or glues, this may be a better option. However, it's your choice as to how you proceed with this. My suggestion is you start with these aliphatic resins, is what they're called, and if you feel comfortable using the instant glues, then go right ahead and do that. Stan suggests using nitrile gloves. I think that's a good idea, and you probably should do that. So here's what we do. We take the glue, we take the part, this is the wingtip. I'm going to run a bead of glue along this wingtip. I don't mind spending a little more glue than is probably needed. However, I find working with youngsters that they like to use glue liberally, probably beyond what it's reasonable to expect. However, you can decide that yourself. So we use the same tip blocks. This is 1.5 inch on either side. We block up this tip, pin it in place. As I said, this stuff takes a little longer to dry. Approximately a half hour. On the wingtips, I would allow even more than that, maybe 45 minutes, because this is a point of some stress on the model, and you want to make sure they're good and cured. So we'll pin these in place. Put the measuring block in, dihedral block, whatever you call it, and we'll just let it set for the next little bit. While we're doing that, we'll work on the fuselage. If you remember, we're going to glue the fuselage pieces together, so we'll do that next. As soon as I find the fuselage. Ah, there it is. Hiding. Once again, there's a top and there's a bottom. We're going to make sure that we have the top on top. Put that in place. Pin it down securely. Mark where the end of the fuselage should be. There. Mark where the end of the stabilizer should be, which is right there. The next step is to glue on the nose piece, same as we did earlier. This is used as the launch point, so it's glued on in this fashion. We'll cut it later after it's dried, so that it makes the diameter of a dime requirement. By the way, I use SIG bond or tight bond cements for just about all of my construction for a couple reasons. One, because it's slower curing, it gives you time to move things around to make sure you've got them in place, in the right place. And the second thing is, I like the idea that I can wash my hands or wash this stuff off easily. It's not that I don't use the others, I do, but I find this to be a little handier. However, the new glues are pretty strong. They work well, and I don't want to discount them either. Okay. Glue this in place. So now we've got the nose piece, which is where we connect up with the rubber band, and I've glued the pylon in place. Pylon is that raised part in the center. At this point, we just have to let things dry. So we'll take a little break while that happens and we'll get back to you. So we've let a little time pass, and I have taken the wing off of the board. It seems to be holding okay. I've glued the fuselage parts together, as you recall. While we were off camera, I marked the back of the fuselage. I know where to cut that off, and I've also marked the circle with the dime so we know how that diameter is supposed to look, like that. So what I'm going to do right now, just like I did on the other ones, I'm going to cut these to shape, and I'll glue the wing on, show you how that's done. So with the use of Sig Bond. Okay? Oops. So cut that to shape, do a little sanding to round it off. I think that's probably good enough right now. Cut off the excess from the back. I don't need that extra weight back there. And now we're ready to glue the wing on. Now, one thing that I did before I took this fuselage off of the building board was I marked where the balance point is. You see this black mark right here. I put another one on the other side. That indicates the balance point. So when we get the wing glued on and the tail, everything finished, we'll balance it up by adding some clay to the nose. And that way we'll have the correct balance. And so that's the balance point. Should be done before you put the wing on. So this is going to be a little bit tricky, because what we're going to do is we're going to use aliphatic resin, or in this case Sig Bond, to glue the wing in place, and we're going to use pins to hold it. As you recall, last time we did it with CYA, and we glued it while we held it in place. This time we're not going to be able to do that. And you have to be careful not to pin yourself. So I'm going to put this down, press against it. These pins have flat heads on them, which makes them a lot easier to push into place. I'm going to do one right up here on the leading edge. Now that's in place. I'm going to try to level it up so that we don't have, we want to have the wing exactly perpendicular, I think that's the right word, with the fuselage. May need to twist that just a little bit more. I'll use another pin to help offset that. Let's see. Not quite yet. We'll bend it some more. There, I think we're right about. It's close enough for this point anyhow, so we'll just let this dry. So while this is drying here, I'm going to glue on the stabilizer. Do that by putting glue in the location where the stabilizer goes, right on the fuselage. It's a little excessive, it looks like. We'll put the stabilizer in place, make sure it's even with the back line, and then I'm going to use a couple of pins just to pin it in place. And once again, we're going to try to have a little bit of stab tilt to the right, So as you look at this, you notice this stab tip is slightly higher than this one. The amount is kind of trial and error. This one appears to be about what it shows on the plans, and I think we'll just leave it there. And while that's drying, we'll go ahead and put the fin in place. Once again, the fin has a little piece of 1/32 scrap that's glued to it. That's it forces the right turn. We'll put this, glue this on with a little bit of Sig Bond. Put it in place. I think it's going to stay. Yeah, it looks like it's going to stay okay. Well, we may end up pinning it just to be on the safe side, but it may not need it. We'll pin right through just to hold it. Yeah, so there you have it. You have the stabilizer with a little bit of tilt to it. The wing's pretty straight on there. The fin has its offset. This will take 20 minutes or thereabouts to dry. We'll just set the model aside. We'll finish sanding. I'll use the other model as a demonstrator so we can show how we sand that the fuselage down a little bit. And while this dries, we'll do that. So here is the model that we built earlier. This is the one that was built with CYA. And I'm going to use a little heavier sandpaper. This is 240 grit. And we'll just sand the edges of the wood down so it's not square. The idea is to streamline it slightly, but more importantly is to reduce weight, particularly toward the trailing edge, the back of the fuselage. The more weight you can save in the back, the less weight you have to put on the nose to get it to balance. And the lighter the model is, the better it will glide. So we'll sand this down. Might try a little bit of the other sanding block. It's finer. It doesn't matter much. It just takes a little longer to sand with this sanding block than it does with the other one. Now on this model, I've already put some clay on the nose. When you buy the kit comes with a wad of clay on it in the kit. This clay is then put on the nose in order to get it to balance. You notice I've got the marks here showing where the balance point is. With the clay on, this model should balance right, like there we go. That's how it should balance, using those 2 points. And that's a good place to start. When we go to test fly this model, we'll find out whether it's tail heavy, nose heavy, or needs some other adjustments. But as a starting point, that center of gravity or that balance point is a great place to start. We may end up adding some more clay to the nose. We may end up taking some clay off the nose. We won't know that until we put the model in the air, find out how it glides, how it flies. So we'll finish up a little bit of sanding, rounding off the area around the nose here. I think some underneath would be worthwhile as well. Be careful not to hit the wing, not to make notches in the wing that aren't necessary. So I think we're basically ready with this model to do some test flying. There's no finish that's put on an indoor model. There's no dope or anything else to finish it off. It is essentially ready to fly once you assemble it like this. In order to fly it, Stan sends along a launcher. This is just a piece of dowel that has a rubber band on it. And this rubber band is used to launch the airplane. When we go to the gym to test this out, we'll use this launcher and see how high we can get it in the gym. And the only thing we're waiting for now is for this model to complete its cure process. Once that's done, we will add some clay to the nose, get it to balance. We'll do a little sanding just like I showed you on the other one to get all of these surfaces rounded off, and it'll be ready to go. So our next session will show you how we trim these out. We'll be in a high school gymnasium for that purpose, and we'll see you there. So here we are at the high school gym. We're going to do a little bit of test flying of these two gliders. Since we built them in the days that have gone by, I have weighed them both and I've put a number on them. So the first one we built, which was built using Cya adhesives, I've put the number 1 on, and I weighed it. Now it's got the nose weight on it, but it weighs 5.3 grams. The other one, which was built with the Tight Bond or Sig Bond, is number 2, and it also has a weight on it. It weighs 5.0 grams, so exactly 5 grams. So the object today is to do some test gliding to see how they glide, and then to do some launches to see how they fly. So we'll start. I'm going to put one of these down. I'll put number 2 down for now. And we'll just start with number 1. The object is to do some hand launch flights with it and see if it stalls or dives. Whoops, looks like it stalls. We'll try that again. Point the nose down a little bit this time and not throw it quite so hard. A little bit of a stall. So Stan's instructions are, if it stalls, there are 2 ways to deal with that. One is to add some additional weight to the nose, which we will do. This is some of the clay that came in the kit. So I put basically a fingernail size piece of clay on the nose. We'll try gliding it again. Much better. Now we'll try the same thing with glider number 2, see if we can get a good glide out of it. Now we're ready for a powered launch. When you buy the kit, it comes complete with a launching stick and a rubber strip. And I'm going to show how to set this up for launch. We'll go back to glider number 1. This is the one that was built with Cya adhesive. Grab a hold of the model back there. Notice that the rubber band is hooked onto this notch in the front of the fuselage. Now you need as much room as you can get in the gym, because you don't quite know what's going to happen on the first launch. So I'm going to go out a little further. I'll launch at about a 45-degree angle, which is how Stan shows in the plans. I'm going to put a little bit of left bank, so you notice that the left wing is down. And I'll pull the rubber band back. It's about 3 feet long. Here we go. Whoops. I'm going to lower the angle of launch a little bit because that was too steep. Maybe 30 degrees. See what happens here. Wasn't turning to the right enough. I put a little more right rudder into it. Try it again. Flat, fairly flat launch. That looks better. Since it appears to dive into the floor, I'm actually going to take some of the weight off. This is the weight I put on earlier. Let's see what it does with less weight on the nose. We'll try another launch. I'm going to increase the incidence of the stabilizer. This means you bend the trailing edge up slightly. You can do this with balsa wood if you're very careful. just by rolling it with your fingers and your thumb so that the trailing edge of the stabilizer is moved up slightly. Let's see what the difference that makes. Come on. So I have set aside model number 1 for a while in order to see whether I can get model number 2 to fly a little better. And so we're going to try a launch with this. We'll start with low power. Won't stretch the rubber band back too far to see just what happens here. These first flights are always a challenge. Correct the stall by adding some more weight to the nose or by bending the elevator down the back end of the stabilizer slightly, just in order to decrease the incidence a bit. I'm going to try decreasing the incidence slightly to see what happens. And by trial and error, I'll determine whether that's the right thing to do or not. We'll come back perhaps and add some weight if needed. Try this again, once again on low power. It was just a hint of a stall on that flight, so I can correct that by adding just a bit of weight to the nose. So it doesn't take much as a rule. This is about the size of my small fingernail. And let's try it again. Low power once again, slight bank to the left. Now the glide on that was pretty nice. The circle was maybe a little bit too tight, but it was also a little fast, which means that it wouldn't stay up as long as you'd like it to. So if we increase the size of the circle, it should slow down the flight. We do that by taking some of the rudder tab that was built into this model out of it. And once again, we just simply bend the trailing edge of the fin, the rudder, a little bit to the left. That means it has a little less right turn. Bend that just with our fingers, like that. We'll try another launch. Once again, about the same as time before, not too much power. Maybe a little more power this time. On this next flight, what we're going to do is add a little more power yet. It still has a little bit of a steep angle in the glide, but it's good and safe. So we'll add a little more power, see if we can get some more altitude, simply by pulling back on the rubber band a little further. It's a little faster in the glide than I'd like to have it, and it still seems to be nose down. I'll take some of this weight that I just added, I'll take it off. We'll see what happens on this next flight. Once again, I'm going to pull it back a little further, see if I can get a little more altitude. One trim technique that we haven't talked about yet is the possibility of adding clay to a wingtip. When you add clay to a wingtip, it adds weight. Weight on the wing tip that you want to have the model turn into. If that makes sense. In this case, I think it's gliding too fast to the right. I want it to open up the glide a little bit, so I take a piece of clay about the size of my small fingernail, and I'll put it on the outside, in this case the left side wingtip, just like that. Now the effect of this should be to open up the glide circle a little bit so that it doesn't glide so tight to the right. It's similar to changing the rudder, but it doesn't have the same effect on the climb. So with that added weight on the outside or the left wingtip, the glide actually was more open. However, at this point it developed a stall. There are two ways of dealing with the stall. One is to add weight back onto the nose, which is what I'm going to do. The other is to change the rudder setting and give it a little bit more turn, but we don't want that because it turns a little bit too tight as it is. So we'll add some clay to the nose. So we've added clay to the nose, we've added clay to the wingtip. We'll see what happens. Pull it back about the same amount of power as we had the last time. It's nice to have a gym that's good size. Grade school gyms typically aren't very big. This is a high school gym, it's a reasonable size. Because of the inability to know exactly what's going to happen with your glider, it's best to give yourself as much room as possible. In this case, I'm going to step further out into the center of the gym floor and see if I can get a better launch. So that glide was too wide. In fact, it ended up in the bleachers. So I'm going to try to tighten it up a little bit simply by removing some of the clay that I put on the wingtip earlier. By reducing the amount of weight on that wingtip, it should tighten up the glide. We're looking for an optimum flight. Sometimes that may not be necessary in competition, but if you're intending to place in this event, having the best flights possible is what you're striving for. So we'll go out and try it again. The best flight of the bunch. I think we're awfully close to having this trimmed to where we want it. Probably it could take a little bit more weight off the nose. That would make the glide a little bit more buoyant. I'll try that. But I think for purposes of the serious trimming, we've pretty much come to the end of the road on this model. So I'll take a little bit more clay off the nose. I just took a pinch. That should open up, should slow down the glide slightly. You'll notice that I haven't been, when I go to launch it, I don't pull the rubber band back very far. This is a 36-foot ceiling in this gymnasium. Most of the gyms that you will fly in have much lower ceilings than that. So it's important that you not put full power in it. All you want to do is have enough energy in the launch that it comes close to the ceiling. You don't want to hit the ceiling because that will upset the glider, and you don't want to put so much power into it that you could actually damage it by having it hit the ceiling. So let's try this again. I'm pretty pleased with how this model is flying now. One of the things I need to do is to give myself more room inside the gym because the last flight ended up on top of the bleachers. However, what's important, I think, is that once you figure out where that location is in the gym, how much space you actually need, that you always go back to that same space. When we've flown in this gym in the past, I actually have a spot on the floor marked where I've launched gliders in the past because I know what their pattern is in the climb, I know what their glide path is, and I want to use as much of the gym airspace as possible because that way I'll get more time. It's not out of the question that in a 36-foot high gym like this, that this model will get somewhere between 20 and 25 seconds of flight time. There are flights that have been made in this gym, once again with a 36-foot ceiling, that have exceeded 40 seconds. I wouldn't expect that to happen with this glider, but it's not out of the question that 20 to 25 is very realistic. So as we built this model off the plans, it calls for a right-hand glide. Typically, when you have a right-hand glide, it means that you have a left-hand launch. And so in my case, because I am left-handed, I have been launching it left-handed. So which means I use my left hand to pull back on the model and my right hand to hold the stick. If you build according to the plans, that's how this model will come out. However, if you're right-handed, as most of you probably are, you would launch it with the right hand, I'll get this right yet, in this fashion, with your left hand holding the stick and your right hand pulling back on the peg. Now, because it's hard to bank a model to the left if you're right-handed, and this model has to be banked to the left, it's important that if you're going to launch it with your right hand pulling back on the model, that you build the fin so that it has its offset to the left. In other words, the fin goes on this side of the fuselage, and the little incidence block that's glued to the trailing edge of the fin goes right there. We put a little bit of stab tilt in it. This one has slight up stab on the right side because we want a right glide. In the case of being a right-handed launch, you simply reverse that. You put the stab tilt slightly to the left, the high point being on this side, and you've already moved the fin to the left side of the fuselage with the offset. That's the primary difference. These were built, as I said, according to the plans that I had, and they're built for a left-hander, which is what I am. Flies better than the other one. So I'm back to model number one. I was having some difficulty with this model earlier. Couldn't quite figure out what the problem was. Since that last episode, I've added a little more clay to the nose, and I'm going to try it with a lot lower power on the rubber. So we'll try it, see what happens here. Also, I'm going to try it with a less bank and less angle. So I'll be launching it flatter, perhaps just like that, and almost no bank. We'll see what happens. I'm not going to give it much power on this launch. Well, that looks a lot better. Because the model's still dived, I'm going to take some clay off the nose, see if I can get it to float. We'll try the same kind of launch that we did before. as soon as I get this rubber figured out. Okay. That was the best flight that this model has put in. If you notice, it had a slight stall to it. I can take that stall out by adding some nose weight, but every time I've added nose weight to this model, it has a tendency to dive. I can also take the stall out by inducing a little bit more turn, which is what I'm going to do. If you remember, on the other model, I added some weight on the outside, that is the left tip, in order to get it to not have such a tight glide circle. In this case, I'm going to add a little bit of clay on the right tip in order to increase the glide circle. So this amount of clay, once again, it's about half the size of my little fingernail, so it doesn't take much. We'll see what happens. I think it's in the launch. Okay, here's what I've discovered about this glider, which is different from the other glider, even though they look exactly the same, that each one has its own characteristics. And so I need to remember, and I write down, how I launch each of these models, because each one is launched differently. This one, I have just a very slight bank, and I don't even give it much altitude. I almost launch it flat. Don't have to pull back very far because it seems to take off and climb really well. That glide on the last flight was about as good as I'm going to get. I could add a very, very tiny amount of clay, but I'm not going to do it because the stall is almost non-existent. All I need to do now is to get a little more altitude, and I can do that simply by pulling back a little further on the rubber when I launch it. So we're going to try that. Notice it's almost a flat, almost no bank to it, and I have very little altitude. It's about maybe at the most 15 degrees, maybe even a little less. Pull back just a little further. So even though this model was the most cantankerous, it appears to have the most promise. It's a little heavier than the one that I was flying earlier. The number 1 is heavier than number 2. Doesn't seem to make that much difference. I'm pretty assured that this model will be the one I would use in competition. It would be my first choice. Once you get to the gym, because each site is slightly different, you'll find that you need to either lower the amount of pull you put on the rubber band in order to accommodate a shorter ceiling, or you need to increase it slightly. If you put too much stretch on the rubber band, it gives it too much power and it upsets the model. So you have to be careful that you don't give it too much. Otherwise, you're going to end up with some unusual characteristics in flight, usually a dive. So I think for all intents and purposes, that pretty much concludes our flight activities with these two gliders. I hope you've enjoyed the presentation, and I hope you're able to be successful in flying for the Science Olympiad elastic launch glider event. Thank you very much.
Well, I'm back, and this will be the last segment of this DVD. In this, I'm going to talk a bit about the event and competition and compliance with rules, things like that, tools, adhesives, and so on. Once that part is completed, I'll demonstrate using the plans that will be included with the DVD. The plans are half size, but they are dimensioned, and what you do is take the dimensions from the plan and mark them on the balsa wood and then cut them out. And after that you sand the balsa wood and so on. So I'll demonstrate that. It's pretty simple. I'll be using the wing as the example, and what I do there is the same basic procedure that you'll use on the rest of the parts, the stabilizer, fin, and fuselage. So with that, we'll get on with the lecture about tools and rules and all that nifty stuff. These gliders are pretty simple. Just a few parts to make and to glue together. Plan to build several models. No two models, even of the same design, built by the same person, have exactly the same performance characteristics. Some of them fly better than others, and you'd like to have a couple on hand so that you can use the best one in your competition flying. And it's good to have a backup model in case something happens to the model you were intending to fly. The follow-on to that is be prepared to repair models when they get damaged, because that will happen. Happens to everybody, experts on down. A lot of damage can be repaired on site using the proper adhesives and techniques. I want to briefly go over terminology of the aircraft itself. Of course, we have the wing span, distance tip to tip. The wing has chord, the distance from the front to the back, also known as the leading edge to the trailing edge. Has dihedral, this angle, this upswept feature at the wingtips, which is helpful in providing stability. Also providing stability are the stabilizer and the fin. These function, think of it, the feathers on an arrow shaft. They keep things going kind of straight and level. And a fuselage, of course, this long, slender member, everything attaches to. They talk about the CG, center of gravity, which is the balance point. And it's the point where all of the weight and mass of the model can be considered to be concentrated. The position of the center of gravity is usually referred to in relation to the wing chord, and is also referred to as a percent of the wing chord back from the leading edge. Where my fingers are touching the model, are about 60% of the way from the leading edge to the trailing edge, and that's where the balance point is. This distance from the balance point, the center of gravity, back to the stabilizer is called the tail moment arm, and it's important for stability. One other feature, geometric feature of the models is incidence, and that's a bit hard to show on a model because it's a small angle. The wing is at one angle here. It's attached to the top of the fuselage. The stabilizer is attached to the bottom of the fuselage, and it has a slight nose down angle in relation to the wing. It might be only a degree or a fraction of a degree, but it's very important to have. Your model won't fly well without it, if it flies at all without it. And getting it just right is a big factor in getting the model to perform really well. So we'll be harping on that a lot as we go through the construction phase. Well, this is my idea of a visual aid. It's trying to make the idea of incidence a little more clear. Have the wing here at one angle, parallel to the top of the fuselage in this case. Have the stabilizer at another angle, and the difference between the two angles is simply the incidence. And on a model airplane, on the gliders like this, it'll be a very small amount. I think on my glider the thickness here at front is like 7/16, and at the back something like 3/8. I don't know if those are the exact numbers, but it's a very small amount. And as I said before, this is important to have. It's what keeps the model upright, keeps it helps it correct from dives, is one of its big things. The next topic I want to briefly cover is tools. And I'm going to start off with a rather unconventional interpretation of the word tool, but that is the rules. This document here is a page from the Academy of Model Aeronautics rules book, and it covers the construction and flying of standard class catapult glider, which is the event category that these models would fit into. And it's pretty brief. Projected wingspan must not exceed 12 inches. Projected chord shall not exceed 3 inches. And the area of the horizontal stabilizer shall not exceed 50% of the wing area. These rules are available on the internet. Go to the Academy of Model Aeronautics homepage and look up competitions and rules, indoor rules, etc. as you go down the line. AMA rules talk about 12-inch maximum wingspan. The Science Olympiad rules talk about a 30-centimeter maximum wingspan, which is just a bit less than 12 inches. The model that we're going to be building conforms to the Science Olympiad rules and therefore conforms to the AMA rules. Science Olympiad rule book is available from Science Olympiad people. They talk about, they call it the elastic launched glider event. And it goes on for 2 pages, quite thorough, quite detailed. And you need to follow the rules carefully to prevent disqualification. You can be disqualified at the competition if you don't meet the rules. You may also be required to modify the model, shorten the wingspan, or do something physically to the model to make it comply. So be sure to follow the rules. Make sure that you get a copy of the rules from your school advisor or coach. It's very frustrating to competitors and competition officials both to have to disqualify someone or make them modify their model on the site. So be certain to work with your school advisor or coach to get the proper rules and to follow them carefully, and everything should go a lot more smoothly when you get to the competition stage. And one last unconventional tool, but it is a piece of required equipment, and that is a eye protection. Competitors, now I'm reading from the Science Olympiad rule book here. Competitors must wear eye protection rated ANSI Z87 plus while in the cordoned area of competition. Teams without proper eye protection must be immediately informed and given a chance to obtain eye protection if time allows. Otherwise, they shall not be allowed to compete. Okay, well, what that means is you got to have something that protects your eyes from flying objects. ANSI, ANSI stands for American National Standards Institute. Z87 plus is their specification identification number for eye protective goggles. It's not clear whether you're required to provide those yourself or whether the competition organizers will provide that, but you need to check that out. Otherwise you don't get to fly. Now to more conventional tools, construction tools. Start off with cutting tools. Probably the simplest is the single edge razor blade. I don't know that anybody shaves with these things anymore, but they are available in hardware stores and building supply stores. I suppose places like Walmart have them also for use in craft projects and building model airplanes. The other kind of cutting tool to consider is the Exacto Knife. It's spelled X-ACTO. It's kind of the standard hobby knife. You should be able to find them in hobby shops. I think I bought this at Walmart. So that kind of store. One thing about Exacto knives is that they tend to roll. They're a nice circular handle, and they tend to roll off of tabletops, and of course things being what they are, they naturally land with the point down in your toe, which is not something you want to experience firsthand. It's simple to cure. Just take a piece of wood, a piece of cardboard, a piece of just about anything, and tape it to the barrel of the knife so that there's a flat surface and it can't roll. It can tumble, but it can't roll. So next is the process of measuring. We'll be working from plans, dimension to plans, that you will transfer to the balsa wood and cut out. So perfectly adequate tool is the standard school ruler, wooden ruler. Has a metal insert in the edge, which is great. It's a good straight guide for cutting, and the metal doesn't allow you to dig in and notch the edge of the guide rather than the part you're trying to cut. This one is graduated in both inches and centimeters, which makes it ideal for the Science Olympiad people. And I think I got this for something like 45 cents at a dollar store or somewhere like that. So that's about all you need, really, as far as a measuring device. Another tool that you'll find useful and necessary is a square, something to make a nice, accurate 90-degree angle. This is a standard drafting triangle. I've seen them in stores that are smaller, maybe half this size, and that's adequate. Another approach is to use the backing on a tablet, a writing paper tablet. They're adequately square. Another item which needs to be mentioned is the cutting surface, or building surface. Just about any flat, smooth tabletop or countertop can be used. The only consideration is that you need to protect that surface from the effects of cutting through the balsa wood into the top of the table. This can be handled several ways. This material is just a kind of plastic cutting surface. Bought it at a food store, Safeway or something. Comes in a pack of 5 with different colors and so on. And one of the advantages supposedly of this is that it doesn't dull your knife quite so quickly as cutting into paper or wood. You'll still want to back up that this material with something like a cereal carton cardboard. Just open up the box when it's empty and lay this on top so that you've got 2 layers to cut through before you get into the tabletop or countertop. If you think you'll be wanting to use pins to hold things in place while the glue is drying or for any other purpose, you'll probably want to have something like a foam core board. These can be bought at, I bought this one at a dollar store, and it consists of 2 sheets of cardboard with a plastic foam in between. Beam this down, it's just a 24 by 30 sheet, about 3/16 of an inch thick, and you can stick a pin in it and it will hold. Next tool or component to consider is sandpaper and the sanding process. Sandpaper comes in several types. There's aluminum oxide paper, there's I think garnet paper, there's black silicon carbide or something paper. Basically three kinds of sandpaper that you'll find in stores, and any of them will work on models. Balsa Wood's pretty easy to sand. The aluminum oxide paper or the garnet paper, the orange garnet paper, are probably the simplest and cheapest and most suitable. Sandpaper comes in various grades. The coarseness of the sandpaper is identified by a number. The lower the number, the coarser the paper, the larger the abrasive particles, and the faster that they'll remove material from the object you're sanding. The coarser grades of sandpaper, this is 80 grit here. This is a good basic designation for roughing out parts, but they also, when you've got them roughed out, they need to be finished up and smoothed with a finer grade of sandpaper. This is, I don't know if you can really see the difference, but this is 220 grit. 220 refers to the number of abrasive particles per unit of square surface. And the more particles you have, the finer they are. The smoother the finish they put on a surface, and you use those for finishing up after the rough work. So 80 grit or 50 grit for rough work, either one will work okay. 180 grit or 220 grit for the smoothing and finishing work. You can also use, this is a Revlon fingernail sanding board. They can be useful for some things on some parts. Sanding blocks are handy for getting nice, straight, uniform cuts, surfaces, finished surfaces, and you can make a sanding block by folding a piece of sandpaper, crimping it at the edges, and folding it over a wooden ruler or any other reasonably flat, level object, and then just sanding away, taking a little bit off the nose of this particular model. And since it's the nose that gets bumped a lot, we won't even bother putting a final finish sand on it. But that something solid to back up the sandpaper can be pretty important. There will be times when you want to put a nice straight edge on a part that you've cut out in order that it will fit up tightly to the adjacent part, and you can have a good tight glue joint, and which will be strong. Fastening is another function. Straight pins are good for holding parts together while the glue dries. What I like to use are just plain old straight pins with glass bead on the head. Another item that needs to be discussed briefly is adhesives. I think that's been pretty well worked over, talked about in Bob's segment. My own personal preference would be to use the aliphatic carpenter's glue. It's easy to work with, it's easy to wash off, gives you lots of time to adjust parts and get everything lined up just right. Its one drawback is that it demands a lot of patience in letting the stuff dry, because it does take a while. And if you get too antsy and try to rush things, well, you invite the risk of parts falling off. But I think the advantages outweigh that one disadvantage. My next choice would be the thick, gap-filling cyanoacrylate, and that would be primarily for repairs on site, at the competition site. If something breaks, you will want to patch it in a hurry, and the ragged edges may not line up very well, so the gap-filling properties of the thick cyanoacrylate will be of advantage. And then once you get some experience with that kind of the thick cyanoacrylate, you may want to go on and use the thinner, faster curing material for construction. But that's my order of preference. That brings us to balsa wood. Balsa wood is a problem in that it's hard to get the good grades that you would like for an indoor model in particular. What you would like to have is for the wings and stabilizer and fin, you'd like to have wood in the 5 to 6 pound per cubic foot category. What you might find at a hobby shop, if you have access to one, is that the wood, if they have it, not all hobby shops are very good about stocking balsa wood anymore, what you'd find is that the sheets probably will be a lot heavier than what you'd like, or a few of them might be about right. It's hard to know what to say about getting how to get the right density of wood. Taking a scale to the store is awkward, might upset the hobby shop owner. The other alternative is that you can order balsa wood from several suppliers. I've used 3 suppliers just to check the quality of their wood and their service, and whether they provide the density of wood that they claim they will. These are A to Z Corporation, SIG Manufacturing Company, and Campbell's Custom Kits. All of them did a pretty good job of providing wood to the density that I requested. A to Z, I requested 6 pound per cubic foot, and it came in at 6 or a bit over, 6 to 7 pound per cubic foot. SIG was also similar in their accuracy of providing the density requested. And Campbell's was a little bit more scatter in the densities, but he also provided the lightest sheets in some cases. These were all measured with a balance beam and so on. I ordered 2 sheets each of 1/32 inch thick 3 by 36 sheets of balsa wood, 2 each of 3/32 inch thick, and 2 sheets of 1/16 inch thick. They all came in a bit over the 6 pounds that they were claiming, but close enough. The service was good. A to Z and SIG came within a couple days after ordering by email. Lee Campbell sent his in about 2 weeks for reasons that are easily explained. So all in all, the service was good. The cost is high for all of them. The costs of the wood were about $10–15. The cost of shipping was $10 or so, 10 to 12. And A to Z has a $15 minimum order. So the order from SIG Manufacturing Company, I think, came in at $25. Lee Campbell was $28. These are shipping and the product together. And A to Z was about $29 and change. So those are your choices. You can order wood over the internet and be assured of getting a reasonably good quality wood. The wood itself is fine, it just may be more dense than you would hope for. But when you're starting out, probably a bit denser product is to your advantage. It's a little more durable and can take a little bit more knocking around. The other option is go to the hobby shop and take pot luck, which if you could deal with that problem by buying more sheets than you need, but that would add to the cost also. So it's pretty much of a devil's choice. Take your pick. There are different types of balsa wood. There's A grain and C grain and B grain. These refer to how the particular sheet was cut out of the balsa log. C grain is kind of mottled in appearance. It's stiff but brittle. A grain has long grain streaks in the wood. It is flexible. It can be bent fairly readily. And B grain is kind of in the middle. Next is the process of transferring the dimensions from the plan to the balsa wood and then cutting it out. As I mentioned earlier, your DVD will come with a 8.5 by 11 sheet containing the plans for a simple model that is legal for this event, for the Science Olympiad elastic launch glider event, and therefore also for the AMA standard class catapult launch glider. I've enlarged those plans a bit. They're still not full size, but they're big enough to get the idea across. What I want to do here is demonstrate how to get from the dimensioned half-size plans to the balsa wood part. And we're going to use this wing as an example. The fin and stabilizer and fuselage will all follow the same procedure of transferring numbers from one place, the half-size plan, to the balsa wood, and then cutting out the balsa wood. So, just going over what's here, you'll notice if you add up all the lengths of the different wing panels, it comes out to exactly 12 inches. That allows you to get 3 full wings out of one 36-inch long sheet of balsa wood. And I would recommend that you get those 3 full sheets out of a sheet. We'll be using 1/32 balsa wood for both the wing, the stabilizer, and the fin. And you would be best to buy 2 sheets of the 1/32 at least. Well, at least one of them might be a decent weight, not too heavy. And if you have a full sheet to work with for the wing, you can get 3 wings out of it, and you can have plenty of room for in the other sheet for another wing and fins and stabilizers to boot. So given the attrition rate of these models when they fly on hardwood floors and so on, you'll probably want to have a few in reserve. Starting out, like I said, the wingspan flat is 12 inches exactly. The requirement for the Science Olympiad event is that the wingspan not exceed 30 centimeters. Well, when you put in the dihedral, this, well, I should back up. The 30 centimeters works out to be about 11.81 inches. When you tip up this outer panel on each side, 1 3/8 inches for your dihedral, the projected span of this tipped up part is now about 2 3/8 for the tip panels themselves. And when you add up the 6.5 inch center section and the 4 3/4 tip panel total, you come out with 11.25 inches projected tip to tip, which is very legal and will keep you from getting disqualified or being required to whack off wingtips or something. So we've got, as I've been saying, we've got 4 panels in the wing, or no, excuse me, 3 panels in the wing. Got a flat center section and the 2 tipped up tip panels. The trailing edge of the wing is straight, so we've got a good simple reference point for our width dimensions. And the length dimensions are just symmetrical about the center line of the wing. The half of the center section is 3.25, so the full center section is 6.5, and each wingtip flat, again, is 2.75 inches. Tip width is, tip chord, to be proper about, 1 3/4, 1.75 inches. The root of the outer panel is 2.5 inches, and the center section is 3.00 inches. So all we have to do is transfer those dimensions to the balsa wood and then glue the parts together such that we have 1 3/8 inch dihedral under each wingtip. That way you will be strictly legal. And with that, I'll get out a piece of balsa wood and go about marking it up for to these dimensions. Okay, I have picked a sheet of 1/32 balsa wood, 3 by 36 in size. This was purchased from Campbell's Custom Kits. Campbell's was the slowest of the 3 different suppliers that I ordered from. It took about 2 weeks. Part of that was because I mailed the order in. I don't have PayPal, didn't want to have PayPal, so I just sent a check in the mail. And also because Lee is kind of a cottage operation. But anyway, Lee is a good guy and we like his products. So to start off, like I said, this is 36 inches long, and our wing blanks are each 12 inches long, so I'll measure those off. I'm using a mechanical pencil with 0.5 millimeter lead in it. Nothing magical about that. Well, I hadn't checked this before, but we get about a 12.5 inch, no, 36.5 inch sheet here. So a little extra to work with. I got the lengths ticked off. I've got my high-tech square here. It's a piece of typing paper that I've used a Sharpie to blacken the edges with, so that it contrasts with the balsa. And I'm just going to make a little tick mark front and back, where we'll cut the 36-inch sheet into 12-inch wing blanks. Okay, that really is a tick mark. Okay, tick mark again, front and back. Okay, I've got all the wing blanks marked off. I'm going to start by trimming the end of this piece of balsa wood. It's a little bit ragged, and since we have plenty to work with, plenty of excess, why there's no problem in trimming it off nice and smooth and square. As far as cutting goes, it's important when you're cutting across the grain, as I am here, so that you keep the blade angle of the blade in relation to the work fairly low, so that you're slicing across the grain. If you try to hold the blade too steep, too vertical to the work, it tends to tear rather than cut, and that's makes kind of a messy joint. You have to sand it smooth and fool around with it. Okay, so one wing blank. Two and three wing blanks. Oh yes, I have to trim the end on this one too, because it was generous. Using the handy dandy 45-cent school ruler with the metal insert. Using the metal insert as a guide for my Exacto knife, so that I'm not at risk of gnawing away the edge of the ruler. Seems to be a hard spot there. Life is full of hard spots. Yep. Trim off some fuzzies there. Okay. Put two of these aside for now. And now we have one wing blank to work on. First thing I'm going to do is mark the center line. Just another little tick mark at each edge. No need to draw a line across. It can, I don't know if it's serious or not, but a sharp pencil can kind of crush the wood when you draw a full line. So I like to use just the tick marks. And then do the cutting with the knife rather than the pencil. So what do we got? We've got the center panel is 3.25 inches on a side. So 1, 2, 3 1/4 from the center line. Three and a quarter again. Three and a quarter on the other half of the wing. Okay, should be 2.75 for the tip panel. About 30 seconds short. And 30 seconds short there, so that's symmetrical anyway. Okay, now let's see, let's start at the tip. For now, we'll put a little black dot with a Sharpie to indicate the leading edge. That will be cut away. And the tip is 1.75 inches from the trailing edge. The root of the tip is 2.5 inches, 2.50. Get that lined up here. 1, 2. Your 1.75 for the tip. And let's see, 2.5 for the root of the tip panel. And I'm lining up with the two tick marks that mark the root of the tip panel. And then we'll, now that we're on that line, I'll mark 2.5 inches from the trailing edge for where we're going to cut to. So, just pretty straightforward. I got the dimensions. Take your flat, straight sheet of 3-inch balsa wood. Measure off the tip panels. And do your math to get the 6.5 inches for the center section. And then from the nice straight trailing edge, measure up 1.75, 2.50, and 3. And there you have the flat pattern. As it notes here, the tip-to-tip span of the wing flat is 12 inches. But when you put in the dihedral, you bring these tips up, it foreshortens the span so that the projected span is 11.25, which is less than the 11.81 inch 30 centimeter requirement. So that aside, start cutting here. Going to cut the leading edge first. It seems like a good thing to do. Yeah, it's easier to use this thing. Okay. One tip panel. I'll start my cut at the root of the tip where the tick mark is so that I don't cut it away again like I did on the other side. There we have the center. Pretty simple, just go through it step by step. I like to lay out the rectangular blank at first, then mark in my joints and cutting lines for the individual panels, and then do the cutting. Seems simpler and just easier for me to do it that way. It may not be easier for everyone. So then what you would do next is do the same thing with the fin and stabilizer and the fuselage. Pretty simple, just go through it step by step. I like to lay out the rectangular blank at first, then mark in my joints and cutting lines for the individual panels, and then do the cutting. Seems simpler and just easier for me to do it that way. It may not be easier for everyone. So then what you would do next is do the same thing with the fin and stabilizer and the fuselage. We talked about incidence before, and that it is important to make your model fly right, make it stable and fly efficiently. On this model and on Stan's kit model also, the incidence is controlled by the front to back taper of the fuselage. Do the best you can and try to get it as accurate as possible. Then just mark it and cut it out, and that controls your incidence is set. When you glue it together, there's not much you can do about it after that. So it's all, once the stabilizer is attached to the fuselage, your trimming, your adjusting for flight will consist of adding or subtracting clay to the nose and bending the stabilizer trailing edge up or down, and working with the fin to do the same thing to adjust the turn. Next would be the sanding of the parts, putting a rounded, just smoothing the part with fine sandpaper on the flat surface, getting rid of the little fuzzies that stick up on the machined balsa wood. You know, they're not very prominent, but they're there, and it's nice to get rid of them. And then rounding the trailing edge, maybe thinning the trailing edge a bit. One way to improve performance when working with a fuselage is to trim or to sand down the thickness of the rear portion aft of the wing. You don't want to go too thin, and in particular you don't want to get it too thin right where the leading edge of the stabilizer attaches, because that's a stress concentration point, and you want to have decent thickness there. As you go farther back, it can come down pretty fine. But what that does is reduce the weight. Reducing the weight back here, back in this part of the fuselage, means that you have to add less ballast to the front to get the CG to come out right. So if you add lead, If you add less clay, you're reducing the overall weight of the model, which will have a direct effect on the duration that it stays in the air. And a general sanding and smoothing, rounding of corners is also a good thing to do. I've run out of things to say, and you're probably run out of things to listen to, so good luck with your endeavors, and have fun, and thanks for listening.